So the next speaker is Juan Manuel Pérez Pardo, who is going to talk about controllability on infinite dimensional quantum systems. So Juan Manuel.
Okay, thank you. So let me try to share the
40
screen
minutes.
first.
You have 40 minutes, okay?
Yes, well, I thought I had 30. So, well, in any case, if I end a bit earlier, that's fine for everything, being the last speaker, so you can enjoy the coffee or the tea, whatever. So let me try to share the screen first. So let me start thanking the organizers for inviting me. It's really a pleasure to contribute in this conference honoring Val. And I really regret not being able to be there in person. I do not like this hybrid modes anymore. There was necessary during the pandemic, but I think we should go back to normal. But in any case, I couldn't make it in person for personal reasons, and I'm happy to contribute in any case, although it is in this hybrid mode. So my talk is about controllability on infinite dimensional quantum systems. So I'm going to report on some recent work and activity that I am doing with Aitor Balmaceda, which is now in Universidad Complutense in Madrid, and Davide Lo Negro in Università di Bari. And okay, this is the menu, the content of the talk. So I will first introduce this control problem in quantum mechanics. So I will present the main goal of all these activities. So we're interested in the context of the development of quantum technologies from the mathematical physics side. And this is why we're interested in this controllability in infinite dimensional systems. So I will motivate why we're interested in this thing. Then for the second part, I will more concretely present what is the kind of problems that we are interested in. And I will also highlight some details in particular, although we are interested in some particular context with applications in quantum technologies. In the end, we have to deal with a very general framework, which is the non-autonomous Schrödinger equation in varying domains. And this has applicability in a much wider range of applications, but I will give more details on that. So even our main focus is this particular controllability problem. The results that we achieve can be used in a much wider context. So I will try to highlight all these possibilities so that, I mean, you can get also a grasp of what is the kind of results that we are getting. Finally, I will just present some concrete applications of the results here on this particular controllability in infinite dimensional systems. So let's start. As I was saying, our aim is to contribute to this development of the quantum technologies, and in particular to the development of quantum computers. So let me just give a brief idea of how this is conceived. And here in the picture, you can see a simplified scheme. What happened? Of a quantum computer. In here, you have just the quantum computer. You start with some finite dimensional state space in which you codify the information. Then you have a quantum system which evolves using some unitary operator. And sorry, this is jumping back alone. I'm not hitting anything. So I don't know if this is. Sorry, okay. Sorry, we let evolve the system with a unitary, and then the outcome of the process of the computation is the state of the system after the computation. So one measures this state, and this is the result of the computation. So producing a quantum computer is producing a quantum system in which one can engineer any possible unitary operator. Okay, so the algorithm is codified in the unitary operator, and this is built out of interactions with the system. So this problem that I just presented is equivalent to the problem of simultaneously control the evolution of n linearly independent states. Why is that so? Well, if I can control a system, and with one set of controls, I can decide how to map n linearly independent states into target n linearly independent states, this allows me to design any possible unitary operator, because I can just fix one orthonormal base at the input and any given orthonormal base at the output. This defines uniquely a unitary operator. So this controllability problem is equivalent to the problem of deciding whether a certain quantum system is a universal computer or not. Now, how is this achieved in practice? So typically, it is proven that for these finite dimensional systems, it is enough to get a set of a finite set of n unitary operators that act on small parts of the system. So they do not act on the full system; they just act on between small regions of the system. Let's say they couple pairs of states, actually. Okay, and it is proven that using a finite number of these gates, this number is actually small, you can build any possible unitary interaction in your quantum system. So you just need to be able to address, let's say, binary gates that couple two-level quantum systems. So this is enough. And this is the key idea behind all the quantum technologies that have been that are developed nowadays. The problem with this approach is that the number of such interactions that one needs to obtain any possible unitary operator in the system grows exponentially with this size of the system. And this brings out a serious scalability problem. So when one is going to double the number of qubits in the system, so the dimension of the states, one do not need the double unitary operators. One needs an exponential increase of the number of interactions that one needs to apply in the problem. And this is a serious drawback of this approach. The problem with this also is that quantum systems genuinely are infinite dimensional quantum systems. So to go back to this picture, to apply this picture, one needs to do an approximation and truncate the system in order to apply the usual techniques of control that one is doing. Okay, so the techniques of quantum control in finite dimensions are well developed. They are well known. They are mainly based on the theory of geometric control theory, which has been developed since the late 60s and 70s. So it's a well-developed theory. The problem is that including this truncation in the system is introducing errors of the system interacting with itself, because you need to neglect the existence of the rest of the levels of the quantum system, which is a serious problem for the coherence. And one of the ways in practice to do that is, okay, if I want to codify in qubits, I will build a quantum system and will approximate it to be somewhat larger than that. I will take some auxiliary levels there, and I will use those levels to control the error that I'm committing with these approximations and also to manipulate the interactions. So the theory of, or the way if one wants to treat the system as a truly infinite dimensional system, one can still stick to the situation in which one codifies the information in a finite dimensional space, but one wants to use the full dimension of the system, so the infinite dimension of the system, to let the system evolve. This is the realm of quantum control in infinite dimensional systems. In fact, this would be a systematic way of dealing with all these auxiliary levels that one needs to address in order to make the computations. But considering the situation of quantum control in infinite dimensional systems also opens the possibility of a completely new type of control, okay? And it's using the space of self-adjoint extensions of the Hamiltonians as the space of controls. This is the boundary conditions. I can have infinite dimensional system. I need to fix certain self-adjoint extensions, certain boundary conditions to determine a physical realization of the system. You can think of the Dirichlet or Neumann boundary conditions, but these do not have a parameter. But for instance, you can think of Robin boundary conditions where there is a Robin parameter. This Robin parameter might depend on time, And a possibility is to use that time dependency to control the state of the system. So there's a new type of control, and this is the way or the kind of situation that we are exploring right now. So to briefly introduce what more concretely what the problem of control is. So this is a typical control problem. I can highlight this. This is called a bilinear control problem. One has one free dynamics of the system. This is the non-autonomous Schrödinger equation. And then one has one interaction with the system. It could be an electric field or something, some potential. And at disposal of the experimental is the intensity of this interaction. So the idea is I want to steer the state of the system from some initial state to some final state t at a given time. And the controllability is to decide whether or not it will exist a control function in this time, such that starting from the initial state, I will reach the target state in that definite time. Okay, so here the solution of the Schrödinger equation is given in terms of unitary propagator, this two-parameter family of unitary operators. So, as I was said just a moment ago, the classic theory of control has been applied successfully to controlling finite-dimensional quantum systems. So, and the success of the recent quantum technologies is a proof of that. So, this approximation that I was saying, although it is somewhat drastic, it has provided a good way of efficiently controlling the state of quantum systems. But we would like to go really to the infinite dimensional case. And what is the way in which they have been applying these finite dimensional results to the truly infinite dimensional quantum system? Well, the idea is let's pick a suitable basis and just truncate the system, constructing some finite dimensional Hamiltonian that approximates the infinite dimensional one. This gives finite dimensional Schrödinger equation, depending on the controls, and one applies the usual techniques of quantum control in finite dimensions to this approximation. Now, one needs to guarantee that this evolution approximates to the true evolution of the system in really infinite dimensions. And this is where this source of errors appears in this approximation. If we want to go to the infinite dimensional setting, unfortunately, the results on quantum control on finite dimensions cannot be extrapolated directly to the infinite dimensional setting. In fact, it is easy to construct examples, or it is very good known that you can construct a quantum system, for instance, the quantum harmonic oscillator. You can consider the truncation in terms of the harmonic basis of the harmonic oscillator. And you can prove that each finite dimensional approximation, so each truncation of the quantum harmonic oscillator is controllable in the finite dimensional sense, but the infinite dimensional quantum harmonic oscillator is not controllable. Okay, it's not exactly controllable in the sense that I was just mentioning. So even the notion of what we will call controllable needs to be rethought if you go to the infinite dimensional setting. And to get an idea of why this happens is, suppose that you have the target state psi t, and that the expansion in the eigenbasis of the harmonic oscillator has countably many non-zero coefficients. Okay, so you need really to have all the coefficients of that state. Then it is clear that if you use the finite dimensional approximation to get the finite dimensional approximation of this state exactly, this finite dimensional approximation will never match the target state exactly. So this is the reason why, even if the finite dimensional approximations of the harmonic oscillator are controllable, why the true harmonic oscillator is not. Okay, this is one of the things that happen in this setting. This suggests also what should be the appropriate notion of controllability that we should consider in infinite dimensional systems. This is the approximate controllability. No, so this will we will aim to get a target state arbitrarily good. So we will say that the system is approximately controllable if for any epsilon, we can reach an epsilon neighborhood of the target state. This should be the appropriate notion. Now, nevertheless, that we cannot directly use finite dimensional control techniques to infinite dimensional ones. A successful approach, which is called legal erking methods, is based on using these finite dimensional approximations to reach the desired target state. The idea is the following. So suppose that we want to control this infinite dimensional state. So this is the true system. And this is the true solution of the system for a given control function u. Now we can try to get an approximation of the system and truncate it, okay? And use the approximation of the solution of the control problem in finite dimensions. So this will give us a concrete u, which is the one who is going to drive the initial state to the target state, or more appropriately said, the approximations of the initial state and the target state. And then we want to use that control and drive to define the time-dependent Hamiltonian in the true state. And this is going to give us this new unitary propagator. Now, the solution of the finite dimensional control problem will be a solution of the infinite dimensional control problem as long as this limit can be taken, right? So this is one of the things that one needs to prove. One needs to get a way of ensuring that when one takes the limit to infinite dimension, the approximations of the solutions of the Schrödinger equation converge to the actual solution, okay? So now, more concretely, I will present now these time-dependent boundary conditions. So to get used to this idea, I'll present here some families of boundary conditions that should be well known, or most of them should be well known. So think that we have just the Laplacian operator. This is going to be our quantum dynamical, the generator of the dynamics of a quantum system is going to be the Laplacian. So we have a free particle in a box, moving an interval, 0 to p. And there are many possible physical realizations on that interval. For instance, I can take Dirichlet boundary conditions. And as I was saying earlier, here there is no parameter, so I cannot introduce any parameter here, but there are many other possibilities. So we can use what is called a delta-like interaction, a point-like interaction. This is given by this family of boundary conditions in which one assumes that the state function is continuous. So essentially, we are gluing the two endpoints of the interval together and building just one vertex. And we are asking for the wave function to be continuous at that point, but we are allowing the derivatives to have some jump, which is proportional to the value of the function at that point, okay? And this proportionality factor is this delta parameter. So this is like having, well, I will go back to this in the next slide. Now, another possibility is what it is called quasi-periodic boundary conditions. Quasi-periodic boundary conditions are like periodic boundary conditions on the interval, but where we have a possible phase change on the wave function. So the modulus of the wave function is continuous, but the wave function itself is not. It can have a quantum phase jump. And of course, one can combine the previous two types of boundary conditions into a more general family of boundary conditions, which we call quasi-delta boundary conditions, in which we can have both parameters, the phase jumps and the delta-like interaction, which behave like an impurity. So just to give a more concrete idea of what these types of boundary conditions represent in the physical system, so the time-dependent delta interaction would be a situation in which we have the quantum particle moving in a spire, and we are introducing some impurity at one point in the spire. And the strength of this impurity, the potential provided by this impurity, is time dependent. So somehow we can control the strength of this impurity, and we aim to control the state of the system just by modifying this impurity, but without introducing any external field. And the aim of this boundary control is that without introducing external fields to control the state of the system, we might introduce less coherence in the system and be able to get better controllability properties on the quantum systems. This is what we hope for. The other type of boundary conditions that I was mentioning, the time-dependent quasi-periodic boundary conditions, remember we have this phase jump at the endpoints of the interval. Actually, this system can be proven to be isomorphic to the following one. Okay, so this is analog to having a spire with sort of periodic boundary conditions, and in which we have a magnetic potential, but that depends on time. And this system is exactly that. So we have here the Schrödinger equation with a term which is proportional to the time-dependent magnetic field. But if I have this time-dependent phase jump, I automatically get also another term here, which is proportional to the derivative of the magnetic potential, and is giving me an electric field acting on the spire whose intensity is proportional to the derivative of the magnetic field. So this is a version of the quantum Faraday law. Okay. Now, in this context, what we have is that we have a Laplacian, we have an operator, and we are going to deal with the non-autonomous Schrödinger equation because we have a time dependence here. But it happens that the time dependency of the Hamiltonian is not only contained in the functional form of this Hamiltonian. So I have time dependence in these parameters here, but I still do have time dependency in the boundary conditions. I cannot get rid of them. The idea of doing this transformation, so remember this is analog to just having the Laplacian with quasi-periodic boundary condition, is that the time dependency that appears in the domain, in this case, we are getting a more complex time dependence in the functional form of the Hamiltonian, but we are going to get a simpler time dependence in the domain. So this is what we are aiming to solve at this kind of problems. And I will be a bit more clear in a few moments of what I mean by simpler. And so we are going to try to address these non-autonomous Schrödinger problems, because this is what is going to allow us to prove this controllability result. But I want to stress here that this type of non-autonomous problems are quite general and go far beyond the kind of applications that we are thinking about. In fact, if you think that you have some free particle that is evolving, a quantum free particle is evolving in a background that is changing, so you can think that you have some manifold, and the manifold itself depends on time, then this situation can always be mapped via certain transformation into a situation in which the manifold is fixed, and the free particle is now described by the type of magnetic Laplacian of this kind. So this is the kind of results that we need. And I want just to stress that even though we are focusing on this quantum control setting, the general solutions that we are obtaining can be also addressed to a much wider variety of problems. So, as I just said, the first problem that we need to face off is the existence of solutions of the non-autonomous Schrödinger equation. So how much time do I have now? I have 40 minutes. I have still 15 minutes, right? Is that correct?
You have 10 minutes.
10 minutes, fine. Of course, there are a lot of solutions available in the literature about the existence of solutions of the non-autonomous Schrödinger equation, but most of them are focused to very concrete families of Hamiltonians. For instance, the Hamiltonians of Schrödinger type. I have the Laplacian plus some time-dependent potential. Okay. In our case, the time dependency is not appearing directly in the functional form of the Hamiltonian, but it appears in the domain of the Hamiltonian. So this is, let's say, the main example about this. I have the Schrodinger equation with the Laplacian. There's no time dependency here, but they have a domain. Think about the boundary conditions that I was mentioning before. So think about the Robin parameter of this quasi-periodic parameter. This is something that fixes the domain of the operator, and this defines a new class of non-autonomous Schrodinger problems. And the most general solutions to deal with these kind of situations were actually obtained in the 70s by people like Toshio Kato, Kicinski, or Barry Simon. But there has actually not been many improvements in this general setting since then. And unfortunately, the conditions for the existence of solutions of the Schrodinger equation that were obtained then are not good enough so that we can apply them to the controllability problem that I was mentioning. They are too strict, these conditions that they were obtained back then. So we need to extend these results that they for 50 years back. So I want just to speak about one of these. This is one of the main results that we were able to obtain recently, and this is a stability result that allows us to guarantee the convergence of the solutions of the non-autonomous Schrodinger equation. Okay, and essentially this result is saying that the result of the evolutions of two different time-dependent Hamiltonians is going to be close enough as long as the Hamiltonians are close enough. And to prove that, we need certain conditions on the derivatives of the Hamiltonian. This is a very natural condition. And we also need this other property here, is being a constant form domain. I will not be given the details, but associated to any self-adjoint operator, you can always associate a certain quadratic form. And the domain of this operator and the quadratic form are intimately related. There's a one-to-one correspondence between them, but the domain of the quadratic form is slightly larger than the domain of the operator. And it turns out that a very large class of problems in which one has time-dependent domains for the operator, the corresponding quadratic form doesn't have a time-dependent domain. So this is the kind of simpler problem that I was mentioning in the previous slides. So doing these kinds of transformations between systems, we can bring one system in which I have a time-dependent, which is a non-constant form domain, into still a problem with a time-dependent operator domain, but a constant form domain. And there is where we can apply this kind of results. These norms are just norms that we can define whenever we have this constant form domain. So I will not enter in these details anymore. And now, using this stability, we were able to prove certain controllability results in the particular case of quantum graphs. And quantum graphs are just a very convenient generalization of the class of problems that I introduced in the case of the spire. So the interval that I gave you with this identification of the boundary condition at one vertex is the simplest example of a quantum graph that one can give. But this can be extended so far. So let me give you more details about that. So this is just to remind you what is the kind of problem that we have in mind. So we are going to deal with a problem which the Hamiltonian does not depend on time, and in which I'm going to introduce a time-dependent quantum phase here. And as I just said, so I will skip this slide. This is equivalent to this type of time-dependent Hamiltonian. And the idea is that if I have a general quantum graph, so a quantum graph is just a graph on which to each edge of the graph I can associate so I have a metric graph. So I associate the Hilbert space of square integral functions on its edge, and I consider the direct sum of all of them. And then I can define a differential operator on the full graph just by taking the direct sum of all the differential operators on the edges. Now, to have properly well-defined quantum dynamics, one has to fix boundary conditions there. Not all the possible boundary conditions are going to define well-behaved, so well-determined proper quantum systems. But there are families of boundary conditions that do determine quantum systems and that are compatible with the structure of the graph. And the most general family of those is what we call this quasi-delta family of boundary conditions, which, if you remember the case of the spar, is essentially the same. So we admit that there are certain jumps in the phases of the wave functions at the vertices. So if I have a quantum graph here, I will have a situation like this. I will have vertices and edges that meet at this graph. So I will allow the wave function to emit a jump in the phase at the edge, at its edge of the vertex. And we will also have some jumps at the derivatives. So this is completely a straightforward generalization of what I just told you. It turns out that in this case, one can always find this kind of transformations that bring the Laplacian into a magnetic Laplacian, in which the domain, operator domain, is still dependent on time, but which the form domain, it doesn't. So let me skip the details about this, but as I was mentioning, the existence, so the relation of time-dependent boundaries that can be connected to magnetic Laplacians and other systems with simpler domains applies in the setting. This philosophy appears here. And it can be proven that all these form domains are constant. So in particular, for these quantum graphs, we can apply the stability theorem that I introduced just briefly before. We can go one step further and increase the complexity of these systems. And instead of considering that they have a graph and consider that each edge of the graph is a one-dimensional manifold, we can consider that each edge of the graph is a higher dimensional manifold. And there is another straightforward generalization of these boundary conditions. So we can admit what we call thick quantum graphs, which are going to be network-like systems in which each edge can be a manifold of an arbitrary dimension, and in which we have at its vertex a family of parameters that we could possibly control, use it to control the state of the system. And now, precisely in this setting is where we were able to prove the controllability result. So the thick quantum graph scenario contains, as particular case, the quantum graphs, and this includes also the case of the magnetic Laplacian on the spar that I mentioned earlier. So these are fairly general result. And we have proven that indeed, if we can use the quantum phases, time-dependent quantum phases, to control the state of the system. So more concretely, so if I have any quantum graph with a Laplacian and I have time-dependent quantum phases, there exists a piecewise continuous, piecewise linear, determination of these phases. This means I can change the magnetic field appropriately on the graph to drive the state of the system from any initial state approximately so arbitrarily close to any target state. And in particular, this shows that I can have any possible graph. You can think we have a lot of loops in the graph. You can think of an array in a chip or whatever. We have this circuit built of this quantum graph. So it is enough to have just one solenoid traversing one of the loops on the graph to control the state of the full graph. This is one of the outcomes of this result. So I was also trying to give some sketch of the proof, but I will skip it. And as a further applicability of the results, to show you that all of this is connected, these kind of problems can be applied to to a much general kind of situation. For instance, suppose that we have a particle in a box with rigid boundary conditions, but that we are able to move the box and to change the length of the box. So this situation is isomorphic to a situation in which I have a Hamiltonian of this kind, in which I have the free Laplacian, and the L is just the length of the interval and D is the position of the center of the interval. So this is another class of situation that falls in the category that I was mentioning before. And we could prove also with a slight modification of the arguments that this kind of system is also globally approximately controllable. So global approximate controllability is what I was mentioning. It was known that the state of the system could be controlled in neighborhoods of the eigenstates. So you can reach any neighborhood of any eigenstate and target any
Juan
state
Manuel,
in a neighborhood of the eigenstate. Yes?
Juan Manuel, I'm sorry to interrupt, but your time's up, so you should try to.
It's my last slide. It's my last slide. So thank you. This so we can prove that any target state is accessible from any initial state. And thank you. This is all that I wanted to share with you. Thank you very much for your attention, and happy birthday, Val.
Thanks, Juan Manuel.
Hi, Val.
I wish you were here, but there are questions. First is that graph model, such things have been used in molecular physics under the free electron model for molecules. You may know it, but at one time, Elisa and I were working on such things. Okay, but
yes, it's like
they have fitted data for binding energies using these free electron models. Okay, so you may want to look. The second is, I think you know the work of Paolo Facchi, Alberto, I think Bebevar on this domain changing boundary conditions on an interval. Okay? Go on changing, then the Trotter formula does not apply, and they have to do things. Okay? So, in that context, I want to ask: suppose you take a disk, then there are the boundary conditions are given by all unitaries of some one-dimensional Hilbert space to itself. Okay? Huge number. Okay, one of them will unitary which winds around non-trivially as you go around the circle. Okay? But there are also Dirichlet boundary conditions, and there is no path from one to the other. So what do you do in that case?
Well, there is no path in the space of self-adjoint extension. You mean? There is no path.
You are Dirichlet, and finally you have one of these unitaries which uses the multiple conductivity of U1 and goes around in UN and goes around the UN once or twice or something. There is no
yes, path. So the idea is the same. So you have so that philosophy is content in this work. So you have a time dependency in the boundary conditions. So in this unitary operator defining the boundary conditions, and the idea is that you can move from one to the other in a dynamical way. That is what we are exploring here. The problem with the changes of topology. So I'm fixing one graph. So a topology is given there, and in these results, I am not allowing from one graph to change into another, which I possibly could by modifying also the boundary conditions. So all these systems are equivalent to a set of intervals, and all the possible graphs are hidden in the possible boundary conditions that I can introduce there. And there are boundary conditions to define one topology and boundary conditions to define a different topology of the graph. But if I want to change dynamically from one to the other, there is a problem. And it's that, so for these theorems to work, for the existence of the non-autonomous Schrodinger equation, there is one very important condition, and is that the Hamiltonians need to be semi-bounded from below. And in this one-dimensional case, all the Hamiltonians are semi-bounded from below, but the lower bound depends on the boundary condition. And the point is, if you want to dynamically move from one to another in a way that is compatible with the non-autonomous Schrodinger equation, so you have to allow quantum dynamics there, the bound needs to be uniformly lower bounded. So you cannot allow this lower bound to drop to minus infinity. And this happens for certain paths in the self-adjoint extension space. You remember from the work that we were doing together several years ago that precisely those conditions which change the topology are those that imply that the lower bound drop to minus infinity, and then there are not existence theorems for the Schrodinger equation that can be applied in that case, or at least it is not known whether this can be done dynamically or not.
Thank you very much for your talk. Let's thank him again.
Thanks to you. Thanks, Val, again. Thanks for the audience. We'll send it to there.